In Unit 5, Homework 1, number 13, we're told that contaminated water is being pumped from a retention pond. R of t is the amount of water that is left in the pond at time t, measured in hours. In Part A, using correct units of measure, find the average rate of change of R of t from t equals 3 hours to t equals 21 hours. And so, given our table of information, what we're talking about is the average rate of change of R on the interval from 3 to 21. So the average rate of change is equal to R of 21 minus R of 3 over 21 minus 3, which is equal to 7,000 minus 17,000 divided by 18, which is equal to negative 5,000 divided by 9, and that is approximately negative 555 to 3 decimal places, 556 gallons per hour. In Part B, we're told to estimate the rate that water is being pumped at t equals 8 hours. Use the correct units and explain what this value means in the context of the problem. So this is an instantaneous rate of change, and it would be the derivative or the slope of the function at that particular value of t. But we have discrete data presented in a table, and if we look for t equals 8, it's not there. So what we're going to have to do is use the average rate of change over the smallest possible interval as an approximation for the instantaneous rate of change. And so what we can say is that the instantaneous rate of change, R prime of 8, will be approximately equal to the average rate of change over the interval from 6 to 9, the smallest interval containing 8. So we go R9 minus R6 divided by 9 minus 6. And that's going to be equal to 14,500 minus 16,000 over 3. And that'll be equal to negative 500 gallons per hour. And let's write a description of this. So we can say that at t equals 8 hours, contaminated water is being pumped from the retention pond at a rate of 500 gallons per hour. And then finally in Part C it says, is there a time on the open interval from 0 to 24 such that R prime of t must be equal to negative 600 gallons per hour? Justify your answer. So Part C is a little tricky, but if you think about this, and this seems to be quasi-realistic data, if you begin to release water from a retention pond or any sort of water storage, it's under pressure due to the volume of water that is being acted on by gravity. And so then what happens is, as the volume of water is depleted, the pressure decreases. And so we would expect the greatest amount of flow to occur over this very first interval here. And you know what? Let's just see what that is, because that's probably going to be our greatest instantaneous or approximation for instantaneous rate of flow. So let's see what R prime of 1 is. Approximately 17,000 minus 20,000 over 3 minus 0, and that would be equal to negative 1,000 gallons per hour. And that's definitely a lot greater rate of discharge than we've seen in either of these two approximations in Part A or B. So here's our argument. Yes, R of t is continuous and differentiable. How do we know that? Well, because they didn't stop the flow at any point when data was collected in the table. So it was a rate of the volume of water left in the retention pond is going to be a continuous function. And it's differentiable because at each point in time there exists a rate of change for that function. So R of t is continuous and differentiable. So by the intermediate value theorem, R prime of t equals negative 600 gallons per hour, because R prime of 1 is approximately negative 1,000 gallons per hour, and water is pumped out on average at a rate of 555.556 gallons per hour. So R prime of t must be equal to negative 600 gallons per hour at least once on the open interval from 0 to 24 hours.